Okay, so I'm going to start off by saying there's quite a lot of content in this week's lessons. So I'm not going to attempt to try and include every little detail because I would be here for hours and I'm sure you would stop listening very quickly. I'm hopefully going to just tackle some of the main points, and then you can spend your time watching the video and working your way through the tasks on the list to hopefully fill in any gaps. So magnetic fields and particle accelerators really follows on from forces on charged particles. So last week we learned about what happens to a charged particle when you put it in an electric field. What we're going to talk about now is magnetic fields. So you covered this a little bit in National 5, but we should remember that electric fields and magnetic fields very much go hand in hand together. So that's why we're kind of leading on. We did electric fields last week. We're going to do magnetic fields this week. So I'm going to talk you through this PowerPoint just now with some of the basics about it. So what we learned about last week is that if a charge is in an electric field, it will experience a force. But there's also something else that happens. Anytime we have a charge that is moving, okay, so it could be an electron or it could be something with 1,000 electrons on it. But as long as it's moving, what happens is a magnetic field exists around about it as well. So again, that kind of hand-in-hand thing, where we have an electric field, we can also have magnetic fields. And it's the interaction of these two fields that basically allow particle accelerators to work. And we'll come on to that shortly. So moving charge creates a circular magnetic field around it, and it can be seen with iron shavings or filings. There's a little YouTube video you can watch about that. Okay, now, the right-hand rule. So this is something that you guys are going to have to be able to do for higher physics, which is use something called the right-hand rule. And it's all to do with the interactions of, because now we've got a few interactions. We've got charges moving, we've got magnetic fields, but we've also got a force experienced by the charge that we talked about last week. Now, the thing about these three things, and we can talk about it being current, field, or force, is that when they exist together, we say that each of them are perpendicular to each other. So we end up with a kind of like 3D graph almost, where each of the things we're talking about are at right angles to each other. So because it's like a 3D concept, it is quite hard to draw, but what you want to think about with your right hand rule is that you've got your thumb going straight up, your first finger going straight out in front of you, and your middle finger going to the left. So it's just a way of trying to represent the three things that are going on and how they interact with each other. Now, excuse me. Now, there is a couple of ways that you can try and remember this. And again, feel free to have a look at YouTube or on the internet and try and get some more information about the right hand rule. But how I remember it is that your thumb, if you think about the letters of thumb, like thrust, and thrust is a force. So that can help you remember that's what your thumb is, the force. Your field, so that's your magnetic field, and the first two letters of field are Fi, and that could be like your first finger. Okay, and then for current, you can think about electric current, and that's the second two letters of second. So EC for second, and that's your second finger. So you might be thinking, that doesn't help, but that's the way I remember it, and it's just like anything else, you just need to practice. So what does this all mean then? Excuse me. So what this means basically is kind of like an equation. If I have two of these things, I can work out what the third one's going to be. So if I know what direction the current's going and what way it experiences a force, then I can deduce what direction the magnetic field is going. And the question that you get asked most about at higher is that you know the direction of the field, you know the direction of the current, and you're working out what force will the charge experience in this magnetic field. So you normally know the first two fingers and you're trying to work out what your thumb is, but it could be other ways. So let's just focus just now on the field, magnetic field. So how would we know the direction of a magnetic field? Well, we can use symbols to represent it, and this is what we've got here. So again, can be difficult because we're dealing with a 3D concept and we're trying to do it on paper. But what we've got here is, if we look at the top, if it's simply going left or right or up or down, then we can just represent it with an arrow showing the direction of it. So that's fairly straightforward. So if my magnetic field was acting down, then I would just draw this arrow, but then I would just draw it to the right if it was acting to the right. So that should be fairly straightforward. Where the issues come is if I'm dealing with the 3D, and I'm saying that the magnetic field is either going into the page or into the paper or coming out of the paper. And how we represent that is, if it's going into the paper, we draw a cross, and if it's coming out, we draw a dot. And again, the way I learned this is, if you think about an arrow, like a bow and arrow, if it were going away from you, you would see the feathers crossing over. And if it was coming towards you, you'd see the point coming towards you like a dot. So it's a way to try and remember it. Now, hopefully this will make a bit more sense shortly. I know it's a lot to take in, but here's an example. So I'm hoping that this is where it will start to come together. So the first thing is, before we look at the question, all of these crosses all together are representing, it's saying that there's a magnetic field present and it's going into the page. So we can see those crosses like the back of a bow and arrow, and that tells us that the field is going into the page. Now, this is a kind of standard question on using the right hand rule. So there's two questions here. Basically, we want to figure out what force the electron's going to experience, or what direction of the force that the electron's going to experience as it goes into this into this field. So how we do this is you use your right hand rule. Now, because your first finger is the field, the way I do this is you kind of make almost like you've got a gun. So you put up your right hand rule and then you point it into your page, because your finger's going in, your first finger's going in, and that tells you that the field is going in. Okay? And then your middle finger is an electron. So because an electron is current, that is going to be your middle finger, and it's going to the right. So you have to turn your hand round until your middle finger is turning to the right, but your first finger is still pointing into the page. Very difficult thing for me to explain without showing you, so I might actually try and refilm this showing you in a minute. But what you should happen, if you've managed to follow that, is that your thumb ends up pointing down. So your first finger's in the page, your second finger is going to the right, and your thumb is going down. Now this tells us that the force experienced, the direction of the force experienced by the electron in this field is down. Now a proton, because it's a positive charge, it'll do the opposite of what an electron would do. So if you work this out for a negative charge of an electron, then whatever direction you get for the electron, the opposite is going to be true for the proton, because that would go in the opposite direction. It would experience the opposite force. Okay, now another sort of little cheat to help you with this is, because I know it can be a bit confusing, especially when you're trying to use your hand, but the way I always kind of think about it is, because each of these things are perpendicular to each other, then none of them can exist on the same plane as each other. Now what I mean by that is, because the electron is going to the right, then straight away my answer can't be left, because right and left are on the same plane. So I've already discounted left. Because the field is going into the page, I can also discount out of the page, because they're on the same plane. So if it's not left or right and it's not in or out, it only leaves me with the option of up or down. Now, what that does is it narrows it down, and you've got a 50-50 chance. And it also means that when you're using your right hand rule, you know it can keep you right because you know you're either looking for up or down. This method certainly takes practice, and like I say, ideally we'd be in class and we'd all be doing this, and it's not the easiest to teach. So hopefully if you all can come on for a meeting this week as well, we can show you some more examples of this. Okay, so there are some questions in the problem book to try this, so again, just have a go and let us know if you need any help. Moving on. Particle accelerators. So this is the purpose of this sort of subtopic, is to learn about how particle accelerators work. Now, if you were in school just now, myself and Mr. McFarlane would no doubt be boring you with hours and hours of talking about CERN, that we were lucky enough to go to a few times. And the reason we'd be talking about it is because CERN houses particle accelerators. That's what they do. They accelerate particles and collide them in the hope of making new particles. So the whole sort of subsection here very much revolves around CERN and the work that they do. So again, might be useful going on to CERN's website and having a bit more, having a read about the information they've got on there and what they do. So very simply though, what do particle accelerators do? Well, their job is to speed up and increase the energy of a beam of particles. So kind of closing the name, accelerator, it wants to speed them up. How they do this is a combination of electric fields and magnetic fields. So it takes both of these fields together and it steers particles and accelerates them. So the electric fields are there to accelerate the particles, and the magnetic fields are there to steer and focus them. Now, this is one of the big outcomes for this topic, and it's a classic exam question. Describe what the purpose of the electric fields and the magnetic fields are. So electric fields accelerate, magnetic fields steer and focus. Now, there are a few different versions of particle accelerator. I'm not going to read you through because you probably noticed we're at 7 out of 42 slides, so I'm not going to go through every single one of them, but I would please urge you to have a read through and watch the video clips to get a bit more information. This one is a linear accelerator, or they're sometimes called a LINAC, and that accelerates our particles in straight lines. Now, that's okay, that works. However, if you're really wanting to accelerate particles and you want them to get up to the speed of light, you're going to have to accelerate them for quite a distance. So it makes more sense to have circular accelerators so that the particles can keep going and not be stopped. And you get two versions of those. This one's called a synchrotron. And what that does is it steers them and accelerates them round in a circle so they can keep going and get their speeds up. Now, at CERN, you are talking about accelerating particles up to 99.9% the speed of light. So they can, again, I would urge you to have a read through of this, but here is a little schematic of how CERN works. Is what you've got is initially there's a linear accelerator which releases particles into the synchrotron, which speeds them up, and then they are released into the Large Hadron Collider, which is the biggest particle accelerator they've got. Now, again, have a read through this. I'll not go through every detail. I'll come back to that in a second. So, so here we've got what the Large Hadron Collider looks like at CERN. So you can see, this is basically drawn over the top of the map just to give you an idea of how massive it is. So you can see here, you've got your linear accelerator coming in here, this straight line. And once it's up to a certain speed, it's released into the proton synchrotron here and is accelerated. And then when it gets to the correct speed, it's released into the Large Hadron Collider. And from this schematic, you can just see how massive it is. It actually borders between Switzerland and France. It actually crosses countries. It's that large, 27 kilometres, the largest one in the world. Now, what happens is that at CERN, they have what we've put is particle detectors at different points in the Large Hadron Collider. So ALICE, CMS, LHCb and ATLAS are detectors that are placed at different points in the tunnel. And that's just really because the scientists are looking for different things. So depending on what particles they're looking to find, whether it's the Higgs or if it's neutrinos, or if it's certain quarks they're trying to find, then they have different detectors set up along the Large Hadron Collider. But you can see here they are released in, and there's different sort of booster rings that they have to go through before they're released into it. So, but all of them have the same purpose, which is to accelerate the particles. But without the magnetic fields, you wouldn't be able to steer them. So it's all designed using the interaction between electric and magnetic fields to allow them to accelerate close to the speed of light. So here's just some information about the Large Hadron Collider. So again, we could talk about this for hours, but feel free to have a look into it yourself. There is a good picture here of one of the detectors, and this just shows you how complex it is. So a good photograph here to show this is where the particles meet. Now, the Large Hadron Collider accelerates protons, so you can think how tiny they are, and look at the size of this, which is designed to detect what happens when they collide with each other. That's why it's the Large Hadron Collider. So the particles are accelerated, they're hit together, and new particles are created. And this is what it takes to be able to detect them and understand what those particles are. Now, I've went through a huge amount of information there, guys. I don't expect you to be completely understanding every single detail about it, but hopefully it at least sets the scene for what the work is going to be this week. Success criteria: define what is meant by a magnetic field, use the right hand rule, state the purpose of the electric and magnetic fields, and then, similar to last week, just solving the problems involving charge, mass, speed and energy of charged particles in electric fields. Okay, so quite a lot of content to go through. You've got your notes as well with the information about the particle accelerators. So again, please make sure you're reading through. I don't think it's going to open, but you've got them anyway. Make sure you're reading through your notes, that you watch the little video clip that we've put on, and most importantly, you try the problems. Okay, so again, any questions, please just get in touch.